start this recording. Oh, right. I'm charging my pencil. Hopefully 15% is enough. Let's see. Plug in my iPad. So much charging going on. All right. Oops, 240. All right. So on Moodle, I posted a couple of things. Let's see. Get logged in. I posted down at the bottom here. Oh, it's weird. Oh yeah, well, you don't have a pointer here, but I posted the Lab 5 solutions, the RMD code, and the HTML. I've marked half of you guys, sorry. But what I'm seeing is that there's a lot of overthinking it going on. But I also posted Lab 6, so if it looks like it's too easy, don't worry, it's supposed to be really easy. And you don't really have to go anywhere beyond this, okay? So, so if it looks easy, then just take it for what it is and just treat it as an easy assignment, okay? Same with Lab 5, but I saw a lot of fun things going on, but definitely a lot more work than I expected. All right, so have a look at those solutions. And I think I saw a question here. Hey, Louise. Not a question, but pleasant just the same. Okay, so all right. So I did have some questions kind of over the weekend if what the quiz would be on. So we've got our Moodle quiz on Wednesday. Moodle quiz on Wednesday during class time. So you'll have the whole class time. I've decided that I'm going to make it all multiple choice because that way we can, you can have your marks right away and that kind of fun stuff, but also it makes it a little bit easier, hopefully. Oh, the book that includes the R coding, so that was what is it called? ISLR, I want to say. Yeah, this one. So it's the Introduction to Statistical Learning, ISLR, and it's just a free book, but it's got all these, so with applications in R. I would say it's a little bit more, I don't know, advanced than what you're doing, so it would probably be like a next step, but still, I think pretty good. Oh, nice. Thanks, Annabelle. Yeah. So that's ISLR. And you can just Google it. So, and you can just download the PDF. Awesome. Okay. So it'll be on everything after test 2. which is chapters 7, 8, and 9. And 9 we're going to do today. 7, 8, and 9, let's say. We did do 7.1, the interactions, but of course, those are going to come up in the rest of chapter 7, so I don't really see the point in excluding 7.1 because you'll use it in the rest of chapter 7 anyways, so that's why I'm saying all of 7, 8, and 9. These are going to be very kind of broad questions, right? And so make sure that you have a look at those review questions that I've posted, the Moodle questions on Moodle questions on Moodle. Right, but I posted those extra review questions as well as your assignment questions, right? Very similar, kind of broad idea type questions, nothing too specific, right? And everything that we've gone over in class, so nothing beyond that. Lab 6, I posted lab 6 is we decided due April 21st because you wanted to have it until basically when our final would have been, but now we're not writing a final exam, right? So, so we'll just use that as our due date. But because that's our final exam date, right, I have to have grades all done and everything. So no late labs will be accepted, right? Or can be accepted because I have to submit your grades. So just make sure that you get it in on time. Okay, so all right, I'll just check in for any questions here first, but let me go over my list. Oh, one thing I wanted to ask you about the format for this, the Moodle quiz. Do you guys have a preference? Like, do you want to have 5 questions per page? Because I know you said for test 1, it was hard with all the questions on one page, but do you want like maybe 5 or 10 questions per page? Do you have a preference? That kind of thing, because I want to lay it out so that you like it.
How many questions in total?
I'm guessing probably about 30 questions.
Yeah, okay. I would suggest at least 10 because if you do it 5, then it will be 6 pages. So I'm thinking, how are we going to track which answers which questions we have answered and which ones we did not?
Yeah, so, well, it should show you at the top which ones are answered and which ones aren't. But so the 30 questions, how about I'll do 10 per page? Right, because then you can go through and you can check just the 3 pages. I think that should work. All right. Let me just check here. See if there's anything else. Good. Good. I'll have to check because, yeah, like you said, you want to be able to make sure that you did them all, but it should put a little like incomplete, complete sort of check mark situation. Yeah, so it's going to be a Moodle quiz. So it'll be the same kind of format as basically your assignments, but longer. Yes, I already answered it, but yeah. So it'll be a Moodle quiz. Yeah, okay, cool, that's good. Good. So it should do that. Okay. But like I said, hopefully I'll test, I'll do a run through, but hopefully 30 questions in an hour and 20 minutes, right? And so you'll have an hour and 20 minutes to do it, right? So hopefully 30 questions in an hour and 20 minutes. I think that's pretty reasonable, especially because they're multiple choice. So don't leave anything blank, of course. But I'll try to make these as simple as I can. Okay. Some that'll kind of stretch your mind, but nothing too crazy, right? Not assignment style. All right. Or I guess your assignments have been pretty easy, so lab style. Okay, anything else before we start our last chapter that we're going to finish today? So we're doing chapter 9, which is on logistic regression. Logistic regression, which from what I understand, you guys have done logistic regression in probably 1 or 2 courses. Definitely with Norm, right? Is what I've been hearing. Yeah. So today should just be basically review then, which is nice, right? Because we're not actually going to go very deep into these things. We're just going to talk about what is logistic regression, and basically that's it. So we'll talk about why we use it, right? And sort of how we use it. So section 9.1 is called choosing a logistic regression model. Choosing a logistic regression model. The key thing to remember is that we've got this categorical response. In fact, we're going to whittle it down to just a binary response, right? A yes-no situation. So we have a binary response. So a yes-no, which will translate to success failure in general. All right, so we've got the success failure response that we want to try to model, right? So our explanatory variable, and we're just going to deal with one explanatory variable in this section. You can keep reading the rest of the sections, right? Chapter 10 talks about multiple explanatory variables. We're not going to go there. We're just touching the surface here, and then we're getting out. And so the explanatory variable can be either categorical or numerical. All right, so we'll be able to deal with both. And so what we're going to do, right, because we've got this binary response, right, so we can change all our responses to a success failure situation, right, and we can do that with a lot of different data. So it's not always the best way to model it, but we can always, or we can usually whittle things down to success failure, right? What we're going to be talking about is we're going to be modeling the probability of success, right? And so we'll have some number of successes over our total. And so we'll be talking about, we will model the proportion, but remember proportion, probability, percentages, those are all the same thing. Percentage is just 100 times the proportion, right? But a proportion or probability, probability, right? These are the same things. All these P's, proportion is a probability, which is essentially a percentage right, with the exception of multiplying by 100, but so all these p's, just remember, those are all the same thing. So you can use them interchangeably, and we do, right? So just remember, so we'll model the proportion or the probability of success. So we use P is the probability, so probability notation of success. Oh. Another way that we could say this is the probability, so P is the probability that y equals 1, right? If we've got a binary outcome. Binary response, response as y equals 1 is a success. Okay. So y is the response, right? If 1 is a success or indicates a success, then the probability that y equals 1 is the probability of success. So what we can do, right, is we've got P, which is the probability of success or the proportion of successes, it doesn't matter. What we can do is we could fit a model, and usually a linear model, right, to P against X, the explanatory variable. And so we might be able to fit a linear model to P against X, right? So the probability of success against the explanatory variable, whatever it is. Okay. But what we're going to find, right, we have to be careful because P against X, well, P is the probability of success. A probability, we have to remember, has to be between 0 and 1, right? And so even if we're able to fit this, so we've got, you know, P here, X here, even if we've got these points and we've got this straight line, here we've got P of 1, here we've got P of 0, but the line, the problem with fitting a straight line to this thing is that the line keeps going and going and going and going, right? And so here what we're finding is that it'll give us probabilities that can't happen, right? And so these probabilities that can't happen, oops, I should say happen, right? Because we need to find, or we need to remember that P is a probability, and so it has to be between 0 and 1. And so we might be able to fit a linear model to this thing, but we need to remember, oops, that probabilities must be between 0 and 1. Between 0 and 1. Oops, I guess I should write that. But the model, right? But the linear model will return values that are outside this range. But the linear model will return values outside this range, right? Which is not good. So what we do is we talk about well, that's where this logistic model comes into play, right? And so now, if we are able to limit something or limit the outcome, so we've got X here, we've got P here, so the probability of success, right, is P. That's what it has been all along. And we limit it to, it has to go from, here at 0, and it can max out at 1, right? What we do in logistic regression is that we put bounds on here so that it has to stay within these bounds. So we get this kind of sort of S-shaped curve, right? Or another way that we could, depending on the situation or depending on how the data looks, right, it might look something like this. Right. So here we've got two different logistic curves. So we need something that's going to force these bounds, right? So that we don't get predicted values outside the range of 0 and 1, right? And so to force the predicted values or the predicted outcomes, to be between 0 and 1, we use the log odds. I did it again, I should write it. 0 and 1, we use the log odds. And technically it's the log of the odds. So what we're going to say is, okay, well, I'm going to let pi be the probability that y equals 1, right? So overall, pi is the probability of success. Right. So let pi equals the probability of success be a probability with pi between 0 and 1, right? Notice that this is not inclusive, right? And so then the odds, actually I'll use a different color here. Then the odds that y equals 1 is pi over 1 minus pi. Okay. Remember odds? Odds are kind of weird because we say the odds are 3 to 1, right? 3 to 1. Or the odds are 14 to 1, right? So now the odds, the larger they are, it's essentially giving you the ratio, right? So it's a little bit trickier than probabilities, right? Probabilities we understand, or proportions even, right? The number of successes over the number of failures. That's not really the case here. Pi is the probability of success. 1 minus pi is the probability of failure, right? And so we've got this ratio here. So then the odds that y equals 1 is pi over 1 minus pi, and the log odds, which we just write as a function, is the log of the odds is the log of pi over 1 minus pi. as always, right, if we're talking logs in stats, especially, we're going to talk the natural log. Right? Oops. Natural log, right, or ln if you prefer. So we've got the log of pi over 1 minus pi. That's the log odds. And so this thing is what we're going to be modeling. Right? And so here, I'll say we model the log odds in logistic regression. It's going to be a little bit more than that, but basically that's what we're doing. So, when we do this transformation, right, because we start at pi, right, pi is the probability of a success, and we're forcing pi to be between 0 and 1, right? We're not interested in the probability of success being 0. We're not interested in the probability of success being 1. There's nothing really to model in that case, right? And so we're able to whittle this down fairly reasonably, right? And then what we do is we find the odds, pi over 1 minus pi, and then we take the log of that, and that's our log odds. So the transformation from pi to the log odds is called the logistic or the logit transformation. So there's two words, they mean the same thing, and so I'll write it down here. The transformation from pi to the log odds is called the logistic or logit transformation. And I'll just say here, logistic or logit. One thing that I thought was pretty cute in the textbook was that they highlight that this is called, if you read it, it's logistic, right? So you don't want to say I don't know how you would say it, logistic. It's logistic, and then more importantly, this is the logit, right? So you don't want to say logit, it's the logit. Otherwise, it sounds like you don't know what you're talking about. So I guess that's helpful. All right, so you want to call it the logistic and the logit. One thing that we're going to use is that, okay, so if we consider a graph like this, one thing to keep in mind, and this is going too deep into math for this course, right? But if we're not including 0 and 1, then this curve is 1-to-1, meaning it's invertible, right? And so we're just going to use that because that's how we're going to go between these two functions. So for all pi between 0 and 1, so not including 0 and 1, I use the secretive we know. It's because we're not going to develop it here, right? It's kind of assumed that you've taken some sort of calculus course at some point, and so is 1-to-1. So therefore, we know that the log odds, the log of pi over 1 minus pi, is 1-to-1, and is therefore invertible, right? This means we can reverse the function, right, and actually get to a real value. what's fun about this thing is that, okay, well, we started at pi. Pi is between 0 and 1, but the log odds actually go from -infinity to infinity, which means that now we don't have that restriction on that we talked about earlier here, right? Now we don't have this restriction on the outputs because our log odds can go from -infinity to infinity, so it can handle any sort of output. So the log odds can take any value from -infinity, can take any value from -infinity to infinity, which means, oh, just a second here, hang on. Sorry, just had to ask a quick question. Okay, so which means we can use a linear predictor, right? So now we can go ahead and use that linear regression that we couldn't before, right? So which means we can use a linear predictor of the form, the very familiar and very basic now, right? Beta naught plus beta 1 x, and I should use a capital X for the population. Okay. So now, right, what this is saying is that log odds log odds, what am I trying to say here? Are how we will use linear regression, are how we will be able to use, linear regression. Okay. So how it works, if we just, and I'm going to do the math, the textbook didn't go through and do the math, but I think it's very simple and it outlines some kind of important things that we'll use, right? And so how it works, right, is you're saying, okay, you've got your log odds, and maybe I should put it in the center here. You've got your log odds, which is, actually, scoot it over. Log odds, which is the log of pi over 1 minus pi, right? That's your log odds. Now we're saying, okay, well, I'm able to, the log odds, I can model with beta naught plus beta 1x. So what I'm saying is that this can equal beta naught plus beta 1x. Okay. So here, what we get, or what we have here, is we call this the logit form, right? That's what we just established. Okay. So what we can do, because this thing is invertible, I can go through and I can reverse this and solve for pi, right? So we can solve for pi, and that's going to get us to a second form of the model. But because we've got this equal sign that we're working with, what we'll say is that these two forms that we land on are going to be equivalent, right? And so we start working through this thing, and if I want to undo the log, and I'm not expecting you to be able to work through, I guess I am sort of expecting you to know the math behind how to unravel this thing and solve for pi. But it's not something that I'm going to test you on at all. But if I take the exponent of both sides, I get pi is 1 over 1 minus pi is e to the beta naught plus beta 1x, right? So here, what I've got, pi over 1 minus pi these are the odds, right? So far I've unraveled to the odds, and what I'm trying to do is solve for pi, right? I've got this little bit of mix up because there's 2 pi's, but nothing we can't handle, okay? So if I'm trying to solve for pi, well, then I get pi is 1 minus pi times e to the beta naught plus beta 1x. Expanding this thing, I get pi is e to the beta naught plus beta 1x minus pi e to the beta naught plus beta 1x. Bringing this pi over to the left-hand side, I get pi plus pi e to the beta naught plus beta 1x is e to the beta naught plus beta 1x. Pulling out this common pi, I get pi times 1 plus e to the beta naught plus beta 1x, oops, is e to the beta naught plus beta 1x. So pi, and let's see if I can buy myself one line of room so it can be on the same page here. There. Pi then is e to the beta naught plus beta 1x over 1 plus e to the beta naught plus beta 1x. This, what we found here, is the probability form. Probability form of the model. Right, so here we've got the logit form, here we've got the probability form, and so it just depends on how you've got this all set up. But remember that these are all equivalent, right, because we've got this equal sign running through, so regardless of if you want to use the logit form or the probability form, you will have the same results, right? It's just a matter of how you plug them in. So, right, these little beta naught, beta 1, right, these will be estimates from your regression, right, but beta naught and beta 1 will come from the logit form, right, and so you're going to be taking the logit form or the logit or the log odds as your response, and then you model it against X, and that's how you're gonna find these estimates for beta naught and beta 1. So some fun facts, right, is that the value of the slope beta 1 determines the slope of the curve at pi equals 1/2. So pi, remember, is the probability of a success. So if the probability of success is 0.5, so 50%. So the value of the slope beta 1 determines the slope of the curve, oops, the slope of the curve at pi equals 1/2. For example, if beta 1 is greater than 0, so if it's positive, then we're going to have a positive slope. Right? So then we would have something that looks like this, right? If beta 1 is less than 0, then you're going to have a negative slope at the halfway point, so it'll look something like this. These were not very good graphs, but I think you get the idea. Because here you've got this negative slope, and here you've got this positive slope. And remember, you're going from 0 to 1, so here must be 0.5. Right? So that's what I'm using. So the slope, of course, tells us if you have a negative slope or a positive slope, and it just is at the halfway point. And so just in general, regardless of if it's positive or negative, as the absolute value of the slope increases, the curve gets steeper. Right. Oh, this should be 2e's. So we've got this kind of as the absolute value of the slope, regardless of if it's positive or negative, as it gets larger, right, we get this steeper slope. And as, oh, not as, that was the wrong line. The intercept, right, for our linear regression here, determines, just like it did for the intercept of our straight line, right, but this thing is going to determine the right to left position of the curve, right? So where is it going to be shifted off to? So beta naught determines the right to left position of the curve. Of the curve. And then just as a rule, the midpoint, right, the midpoint here is going to correspond to an x value that's at negative beta naught over beta 1, and that's just a rule. So the slope tells you something about how it behaves at pi over pi is 1/2, right? Pi over 2. Now I'm talking trig, yikes. But the midpoint, where pi is 1/2, right? So 1/2 corresponds to x equals negative beta naught over beta 1. Okay. So what that looks like here is, let's say you've got something like this. 1, then I guess this is 1/2. Okay. If we've got a curve that looks like this maybe, then the x value at this point, x is negative beta naught over beta 1. Okay. Remember we said that the slope here, it's not the slope at this point, it just is able to tell us if we're increasing or vice versa decreasing, right? And so it'll just tell us about the slope, and then the magnitude of the slope tells us how steep it is, right? But the actual slope of the curve at that point is going to be beta 1/4. That's just the rule. Oops. The slope of the curve at the midpoint is beta 1/4. Right. So here, this is what we call the midpoint. And what we also added was that the slope is beta 1/4. Okay. So we can get a lot of information. We can get a pretty good idea of what this graph looks like, right? Just from, it's a little bit sneaky because it assumes that we have beta naught and beta 1, right? Which we don't have yet, but you can easily just find it in R, right? You just write your logistic model, which I am assuming that you've seen some logistic output. So I just want to kind of fill in the gaps probably a little bit more than anything else. Any questions before we go to the next section? which is the odds ratios?
None so far.
None so far. Not seeing anything in the, good. Okay, good, good. Is this all, I'm so curious, is this all familiar or?
Oh, probably the how you approach the to find, well, the pi on finding the pi. I think it's the same.
Mm-hmm. Yeah.
But the midpoint, I'm not sure. I don't remember the beta 1/4. I'm not sure.
Yeah. So I guess that's where the stats part comes in, probably. But we will see. We will see. Okay, so cool. Oh, I had a bunch of notes here, but I'm actually going to cut them. So we are doing a kind of a quick version of this section because I just want to introduce it and have it. But so that's why I'm going to skip the empirical logit. And I'll just put this on a new page here. 9.2, the actual logistic regression and odds ratios. I'll cut this. So what's kind of fun is that if we remember, so the fitted slope, which I mean, we could call it beta 1 hat if you want, right? I'll just call it the fitted slope, which is just from your actual output, is essentially rise over run, right? Oops. Of your regression. So as a fact, that's going to be the change in the log odds over 1 minus 0, which is the change in the proportions. That's not the important part, right? This part you can kind of ignore. It's just there for completeness. But what we will say is that, okay, well, that's the same as saying that the fitted slope, which is the rise over run, right? So just replacing that rise over run with the fitted slope, and the change in the log odds over 1 is the log of the odds ratio. So if we solve for the odds ratio, right, then we're going to get e to the power of the fitted slope. So what we get, therefore, the odds ratio, just swiveling over to the other side, is e to the power of the fitted slope. Okay. So the odds ratio is a little bit weird, right? Because it's a ratio of odds, but an odd is a ratio itself, right? So you get a ratio over a ratio to get the odds ratios. So we need to know how to interpret this thing. So what we say is that a unit increase, or I should say a 1 unit increase, just to emphasize that it's just one. So a 1 unit increase in x, right? That's the definition of the slope, right? The definition of the slope is for each unit increase in x, we'll see a slope increase in the predicted value of y. That's from just straight linear regression. So now we're saying a 1 unit increase in x is associated with an e to the fitted slope fold, right? So if e to the fitted slope is 5, right, we would say a 5-fold increase in the odds of y equals 1, right? Y equals 1 is a success, right? And so here we're talking about, okay, well, I can use the fitted slope to find the odds ratio, and how I interpret that is a 1-unit increase in x, whatever x is associated with that number, so a 2-fold increase in the odds of a success, or in general, y equals 1. Okay. That's the only thing that I would say that you need for from this section here. There's a lot of other stuff in the textbook, and you're welcome to go through it and check it. But for us, like I said, we're just touching on some core basics here. And more importantly, what you need in order to answer the lab questions, right? So I posted lab 6 here. So you're given some data, walking the dogs, which I thought was pretty cute. And so you either walk the dog or you didn't walk the dog. There's a lot of days where they didn't walk the dogs. Hopefully someone else walked the dogs. But it's, yeah, probably. And so you're going to write down the estimated versions of both the logit and the probability forms of this model. We just went through and did that, right? It does require that you have the slope and the intercept from the linear regression, right? And so make sure that you get those, and then you'll be able to morph between the logit and the probability form. Then part B, use the estimated slope from the logistic regression, right? So here we've got the fitted slope to compute an estimated odds ratio and write a sentence that interprets this value in the context of this problem. That's what we just did, right? And then what would the estimated model say about the chance that a dog was walked on a day with steps equals 4? Now you're just using the probability model or the logit model, whichever one you prefer, in order to do that question. And then for the 50-50 chance of the dog being walked, right, for approximately what number of steps would we have roughly a 50-50 chance? You could look at the graph if you've got a graph, or you could solve it algebraically, right, because that's the midpoint. And so you know how to do all these questions already. So everything after this is just kind of extra.
I have a question regarding D.
Let me see if I can turn you up here. Okay, now I hear you, I think. Say that again.
The question D says what is the point for the 50-50 chance? So can we take just beta 1 by 4 as the point?
So yeah, so for part B here.
Yeah, part D. Yeah.
Hang on, let me see if I can, because I've got the lab here too. So use the estimated slope.
No.
Or this one.
D. Yes.
Yeah. Oh, sorry. D as in dog.
Yes. D as in dog.
So here, this is the midpoint, right?
Yes.
So you want a 50-50. So you want to find what number of steps. The number of steps that we're using is your predictor, right? So that's your explanatory variable. So you want to find the x that is at the midpoint, which is what we did here. Here. So the x that's at the midpoint is negative b0 over b1.
Then what does the next point says? The slope of the curve at the midpoint is.
So that, yeah, so that's the slope at the midpoint.
Okay.
That's just an extra thing that you might not really need. right? Because that's just the rate of change at that point, right, at the midpoint. But here, we want to know for approximately what number of steps, which is X, would we have a roughly 50-50 chance of the dog being walked.
Thank you.
I think it might be easier to solve it just algebraically.
Yeah, but the midpoint, Emily, isn't it? If you have an S-shaped curve, right?
Yeah.
The midpoint, your slope is 0, right?
No, the slope is beta 1/4 at the midpoint.
Okay.
Because these are as a rule. At the midpoint, you're at X, so then you're at a probability of 0.5.
All right. I understand.
And then you've got your beta naught beta 1. So at the midpoint, we've got this information.
Right.
So I would say the hardest part of this lab is getting your beta naught and beta 1, right, from your logit, right? After that, everything else is pretty straightforward, I would say, right? And I'm assuming that you guys have used R to do logistic regression. Has Norm made you use R? Or whatever, if you use Minitab or whatever, I don't know. Anyways, I would say that's the.
You want this entirely on R or handwritten?
I think it should be done in R, just because finding the estimates would be very difficult.
How do you think you can get the database into handwritten thing?
Say that again, sorry?
How does he think that he can get the walking dogs data set into manual thing and do it?
Well, I guess you could do it technically, but it's not something that I want to do.
Yeah, there are 233 data points, so which is not a wise choice to do that.
Yeah.
Now,
so I mean,
yes,
it's definitely possible, but it's not something I would recommend.
Okay.
I think you're better off just figuring out how to do a logit transformation in R, and then finding your beta naught and beta 1. Cool. Oh, that was it. Okay, so for the rest of it, it's not something that I'm expecting to see in Lab 6, right? You've got everything that you need for Lab 6 here. But we're going to keep going just for completeness sake. 9.3 is assessing the logistic regression model. And again, we're not going to go too deep. There are more aspects to it, but assessing, we're just going to do what we need, the logistic regression model. First thing we have to do is we have to argue that we have randomness and independence, which you've been really good about doing for all the labs, so I'm really pleased about that. So argue randomness and independence. If you're curious about some examples, because there are situations where the randomness and the independence is a little bit wishy-washy, right? And so what you can do on pages 434 to 436, it goes through and it talks about a bunch of different examples and how you would argue it for each of those. And so see pages 434 to 436 for examples, right? So if you're having a hard time with that, then it's good to see how they approach some of those arguments, right, of randomness and independence, even if it's not obvious that things might be independent, right, they go through and they just kind of highlight, you know, here are some things that we can say, and feel free to adopt some of their terminology, right? If you're finding that, oh, that was an elegant way of arguing randomness when it wasn't obvious to me, then that's always good too. The second thing that we have to do is we have to check linearity, and we're not actually going to look at it too closely, but there are two different situations, right? And so I didn't want to change colors quite yet. So if we have binary predictors, right? So if we have a binary response as well as a binary predictor, then the linearity is automatic. Linearity is automatic. We essentially only have 2 points, and we're connecting these 2 points. Only have 2 data points. So connecting these 2 data points will be a straight line. So if you have a binary predictor, which is pretty rare, but it can happen, then the linearity is automatic. If you have a quantitative, or I usually call it a numerical just to emphasize, if you have a numerical predictor, you use an empirical logit plot, which we will not really talk about, of the log odds, but you can still make one. You can get the log odds against X, right, and check for linearity. Yeah. We won't cover more than this. There is more, right? And you can see it on pages 431 and 432, right? It does go through and it tells you what to do. It involves kind of, well, it just goes deeper than what we need. Right? So this is what I want you to know, right, is you would use an empirical logit plot, which is just the log odds against X, to make sure that you've got linearity, which makes sense, right? If you're thinking about a regression situation, here the log odds is just the response. Why? Because we've got, right, we've got the log odds is beta naught plus beta 1x, right? So the log odds, oops, against X should be linear, right? Just because of how we built this model, we assumed that we had a linear regression, and so the log odds against X should be linear, and that's all we're using here. There, like I said, there is more, but I'm not going to go into it because we don't need it for this course, because this course is done. We'll leave it for another course. How about? Okay. So the last section is about formal inference. There is more than this, but I'm just giving you, you know, a little bite size enough to get you through if you need it. But of course, the textbook talks about it a lot more. 9.4, formal inference. Tests and intervals. So we are going to hinge a lot of our a lot of our inference on the slope, right? The intercept is not, I don't care about the intercept, right? I use it, but I don't care about it. So this is going to be a lot like just inference for regular linear regression or even simple linear regression. So to test whether the slope in a model with a single predictor, but from, you know, chapter 3 or wherever we started talking about multiple regression, we could talk about multiple regression or multiple predictors, but that's for chapter 10, which we're not doing. And so with a single predictor, so we're just talking about the single case, a single predictor is different from 0, is different from 0. Our null hypothesis is, of course, that beta 1 is 0. We have to assume that it's 0, but I actually suspect that it's not equal to 0. Right, that's our null hypothesis. And then our test statistic is what we compute to test this theory. And Z is in your output. So this will be included in your output. So when you get your slope and your intercept the estimates, right? Beta 1 hat over the standard error of beta 1 hat. Oops. Hat. And these are also from your output, or in the output, I should say, because you don't actually need them, because the Z is actually in the output as well. So you can just use Z. You know, Z follows a normal distribution centered on 0 with a standard deviation of 1, all that fun stuff. So assuming we have a reasonably large sample, with independent and random outcomes. So with independent and random outcomes, the p-value, right? The p-value that comes from a Z, right, is from the normal distribution. So the p-value is determined from a normal distribution This Z statistic is also called the Wold statistic. So when it's in reference to a logistic model, right, or a logit transformation, then we call it a Wold statistic. So this Z statistic is also called a Wold statistic. Is also called a Wold statistic. So a confidence interval, we can build a confidence interval, and I guess the textbook uses the Minitab output because it gives you the confidence interval in it by default, whereas in R, of course, we have to tell it that we want to see the confidence interval. That's fine too, but the confidence interval for the slope is beta 1 hat plus minus Z star, usually 1.96 for 95% confidence interval, times the standard error of beta 1 hat. Oops. So not hard, just kind of uses the output, or if you just tell it that you want a confidence interval. So it's an extra, oops, extra command, oops, in R, or can calculate, I'll say by hand, but obviously I mean to use R, by hand in R, right? Easy enough either way. So here, this is where I'm gonna end this thing, because the rest uses the likelihood. I don't think that we should be talking about the maximum likelihood estimators without a pretty thorough refresher in calculus. So we're not gonna do that. And so we won't talk about the likelihood in this course. But of course they do talk about it a little bit, but even they say, oh, well, you know, that's beyond the scope of this. We put it in chapter 11 for anyone who's interested. But on that note, so we won't talk about the likelihood in this course, and that is the end of all the material. The end. Ta-da! Pretty good. We did it, guys.
Yay.
Yay! I would be sad if we were meeting in person, but it's been kind of weird to just meet online, so I'm pretty thrilled to be done this material too. But I will miss you guys. Let's see here.
We still have 2 more stats.
I know, but I don't think I will get them. I'm not sure. But I'll see you guys around. Yeah. So anyways, so next class, what I'll do is I'll be in the Zoom room if you have a question during the quiz, right? And so I'll just be here, but I'll probably just have my laptop open, not really sitting at my desk. So if you do have a question, then just unmute yourself and kind of get my attention. I know you still have lots of stats, so that's good. But this course I think was pretty fun. Hopefully you thought so too. But yeah, awesome. I know, and I'm glad they're making you take stats. It's important. More theory than I'm sure you like, but still. All right. So, nice. Okay, so like I said, I'll be in the Zoom room, but you'll have to kind of flag me down in some way if you have a question during the quiz. But otherwise, yeah, good luck on Wednesday. And if you have any questions, let me know, but just work on that lab 6 that I posted, because you'll be able to do it all from basically the first half of the notes. All right. Any questions before I boot us all out of here? Nope. Nothing. All right. Oh. I think so too. So just be in touch. If you have some questions, then let me know. But otherwise, yeah, I'll see you guys. Well, I guess I won't see you at all. So good luck. It's been a pleasure. And I'll see you in September. Thanks, guys.
Thank you.
See ya.